Okay, hello everyone. Just a few hours back, I recorded a detailed video about coding a neural network for predicting bigrams in our next character prediction problem. Uh, but unfortunately, the audio didn't get recorded. Right now, I'm just going to quickly walk through the code, what is happening inside it, and then we'll continue on the detailed explanations and further topics. So yeah, this is what a neural network, basic neural network looks like. You have an input, multi-dimensional input. Then there will be a hidden layer, which will be receiving inputs from each of the dimensions of different samples. Then, so each neuron will receive inputs from each dimension of a sample, and then they will be outputting different logits, or what we can interpret as log counts, then convert them into, using softmax operation, we can convert them into probability distributions. So let's see, in our problem where we were predicting the names character by character, let's build the data. So let me quickly show you the uh, data again. So this is the list of names in our data set. Emily, Olivia, Eva. Now we want to build a generative model that predicts these names, right? Therefore, so for neural network, we'll have inputs in a different format, X and Y's. X will be the inputs going into the neural network here, and Y's will be the targets for calculating loss against our predictions. So here I just showed how the input-output X and Y pairs would look like for a word. We append a dot as ending and starting tokens with the word, and we zip them to iterate through each bigram pairs. We convert for both the characters in the zipped format into their indexes. So for converting indexes, we are using S2I mapping. S2I mapping was calculated in our previous video in the count-based method. So if you see here, we evaluated the vocabulary by finding unique characters in the data and making a list out of it, plus a dot. So it was all the alphabets, 26 plus 1. So the length of vocab is 27. Then we made a S2I mapping, which if you give characters to it, it will give the integer index of it. And you I2S, if you give integer index of the character, it will give the character string. So this is what S2I looks like. Now, once we have the indexes here, we append ix1 as input into x and ix2 as output into y. So x and y, we convert them into tensors. So what do they look like? Let's see. So each of them have size 5. X is this, y is this. So for word Emma, we'll have, let me also print this here. So yeah, we'll have 1, 2, 3, 4, 5. These 5 training pairs. X is on the left, Y's are on the right of the dash. So if you see here, X, when X is 0 means dot, Y should be E, means 5. When X is 5 means E, Y should be M, 13, and so on and so forth. So here we have in this integers, X and Y is in the form of integers, but neural networks doesn't take the integers as input. It takes floats, and these integers wouldn't mean anything much to a neural network. So we need to define a way to for a neural network to understand. So one of the most straightforward ways is to convert these integers into one-hot vectors. One-hot vectors is, it will generate a vector of length of number of classes, or say example number of vocab size in your data, and then the the element at the index denoted by this integer would be 1. Otherwise, all other elements in that vector would be 0. So it can be expressed using this one hot function in Torch. So this is how you get it. X inc, by doing this, you will get of shape, because X shape is 5. And for each of these integers, it will pluck out a vector of size 27, because we gave vocab size as number of classes. So X inc size will become 5 by 27. Yeah. Now we have one hot vectors for each 5 training examples going as input. Now we need a way to transform them into different dimensions where it can generate probability distributions for each of the 27 characters in our vocabulary. So we can use a weight matrix which takes in 27 dimensional input and gives out 27 dimensional logits, basically, which can then be further interpreted and further transformed into probabilities. So we do initialize a random weight vector, which would be 27 by 27 size, and requires grad equals to 2, because further we'll see while training we'll use a dot backward function from PyTorch, which necessitates for weights are update the weights that are to be updated to have required grad feature equals to true. Then only they will be their dot grad attributes or methods would be called and evaluated. So what we do in our training side is, first we evaluate. We have weight matrix. We have X. We calculate logits, which is matrix multiplication of X and W. So this would give us same 5 by 27 shape of logits. Logits can be exponentiated and then normalized to get the probability. So this two line of uh, operations are together called softmax, and we can also replace these with f dot softmax method in Torch. Once we have probabilities, we pluck out the probabilities of the correct indices that are denoted by the y's. The indexes that are given by y's, which you see here, 5, 13, 13, 1, 0. So because this probability is of size, the size of this will be 5 by 27. So for each example, each sample, there would be a probability distribution of length 27. So from each probability distribution, this will pluck out that particular probability of the correct index given by y. And once we have probabilities for correct indexes from each examples, we take log of each and we calculate mean over each of those. And with negative sign, this is nothing but negative log likelihood that we also saw in the detail in our previous count-based Bigram model. Once we have our loss, we zero down the gradients of W and we run loss dot backward. Once we have loss dot backward, W dot grad would have been calculated now. So we multiply it with a learning rate and we update the data in the W's. So this is a weight update performed. And we run this sufficient number of times so that our loss increases and goes to a global minimum. Now here we might not be looking to do that exactly, but yeah. So we have xinc. Let's calculate initialize W. Now let's train our data for train our weights for 10 epochs. We have W updated. Now let's do a sampling. So for sampling, it's more or less same as what we are doing in the count-based method, except that the probability distribution was coming from through the count matrix and normalizing it. Here we'll have to perform the forward pass through the neural network that we have built. So we're starting index is 0. For that starting index, we'll have to get the one hot vector. We'll have to calculate logits for that sample, for that one index. Then exponentiate it and normalize to get the final probabilities. Once you have the probabilities, we'll have to sample integer out of 27 integers with this probability distribution, and we append the character corresponding to that index sampled into the out. Once we have uh, appended it, we keep on doing it until ix is equal to 0 again, means we are reaching the end of the generation, and we print the names. So you see, yeah, it's printing 5 names, but everything is Amma. So I think the problem is that while building our data, we took only one word. So now let's just stop printing here. We build the data. X shape, Y shape is this. Now no need to print the X and Y's. It's like 228,000 data samples. So we build F, and we build one hot encodings for each of these. Xinc. Initialize the weights and run the model for say 50 utterances, 50 utterance. Yeah, so we were able to reduce it a bit, not much though. Okay, so 2.4772. Now let's generate names. Looks weird. Rory, Aham, Grir. So this looks nothing sensible as of now, but if you compare these to what random generation would have done, this and the previous two models, this neural network and the count-based model generations, if you compare them to the random generations, you'll see that it is doing something sensible. So how do we generate random generations? We take a probability distribution of the shape as it was in a count-based method. We counted the bigrams and filled those matrix with the counts and converted those matrix into probability distribution for each rows. But here we take all of those as ones and thus just multiply with 1 by 27 because they are 27 vocab size. So we get a uniform distribution across for each character, means each rows, and this is a P matrix. While generation, we just index P of Ix, and it is all same as the count-based generation. So when you do this, you see that this is much more jumbled up generation, which is more nonsensical. Therefore, that's when we can analyze and say that our methods are doing a bit better than this random generation. So I'll be stopping this video now, and we'll get into the further complexity of calculating these logits. So most of these function will be more or less same, but this is what will start getting complex going forward. Thank you.